My name is John Holland. I'm the president and CEO of Paragon. What we're going to accomplish in this session is talking about what to fear and what not to fear about artificial intelligence. For a lot of people, they know it's a buzzword, they know it's the latest and greatest thing, but at the end of the day, it seems like magic. So my hope is when you walk away from this, it won't seem quite as much like magic. What I usually like to start this with, because it's the only magic trick that works in a large crowd for me, I'm going to have you all participate in a magic trick, and hopefully you'll see the parallels. So if you would, all join me in putting your hands directly in front of you. Thumbs up. And put your thumbs down. Put your right hand over your left. I want you to clasp your hands as tightly as possible. Okay? Make sure nobody else is cheating. That's the most common problem you got to deal with. I want you to take your hands, I want you to turn them straight side up. Now, none of you actually think I'm a wizard up here. Maybe not everybody understands how I did that. If you repeat it 2 or 3 more times, I think you will get what happened there. So, AI is a lot the same. It seems like magic. It's how did you do that? That's not immediately apparent how it works. It does some amazing things. It does some things that seem odd. So my hope is when you walk away from this session, you'll have some idea of at least what might be going on under the covers. Stuck this in my pocket for that. Perfect. We're going to start with some of the high-level excitement about some of the products that are out in the world that have something called generative design, what I think is the most applicable and the most exciting about the future of this industry. If you've heard of TestFit or Branch 3D, these are 2 companies that I really liked what they had on their website, so I was able to quickly just grab a quick screen capture of what they're demonstrating. I think this was a LinkedIn page. This is putting in the parameters of trying to figure out for a developer what's the best use of this lot. I want this to have a certain amount of density in housing. I want this to generate using modular techniques. I want it to have whatever parameters. And you'll see it's populating down there the different options that could be used to fill that space, optimizing based on those parameters. So that's a loop. We'll watch it one more time to give you a sense of how quickly some of these things work. It seems like magic. We've just had several buildings just generate in front of us based on just fit it in these parameters, how much parking we need, how tall it's allowed to be, and so on. You'll notice this generative design. I know I mumble. It's a family trait that my father passed on to me, so I'm going to attempt to speak loudly and make sure everybody in the back can hear me. Another one that I'm impressed by is called Branch 3D. Working in mass timber, they have a software that generates what these structural elements need to be like. So you'll notice then pretty close to real time, as they pull this up to multiple stories, what's actually required for the material properties of the columns, of the studs that are in it. That's the stuff to get excited about. Take a quick turn and talk about how machines actually learn. So this is something I hope you can go home and replicate with your children, with others. It shouldn't be as difficult as it might otherwise be. The normal explanation, the education I got in artificial intelligence, was using regression models. They're a little dry, and I am not going to use them. We're going to use something else based off of Donald Michie. He wrote a computing tool in 1963 for solving tic-tac-toe, and it ran without any electronics. It was entirely made out of matchboxes. So what you can see there is a lot. It's over 100 matchboxes that determine this is what the computer would play in response to a human choosing this. So it plays against a human. You would choose a spot on it, and it would choose the next move for the computer. I have gotten us something similar. We don't have time to do all of tic-tac-toe, but we do have time to take my adaptation of rock, paper, scissors. So this little robot, as we're going to call it, is my little friend. He's going to represent our little robot, and we're going to teach him how to play rock, paper, scissors. There are different marbles that I have in each of these 3 drawers. These 3 drawers are titled rock, paper, and scissors. These marbles have different colors. So first, red rock. The point was to be alliteration. So red means rock. I have written on there. You can't read that from here, but if you come up and play with this later, you will see these are rock. Silver is for scissors, and purple is for paper, as you might have suspected. So those 3 things are going to represent the choices that our little robot can make. But it's up to him to figure out what he wants to play in response. And it matters that I stick this back in the right box. Perfect. So the way this is going to work is, it's important to say before we start, there are 6 marbles in each drawer for this example. So 2 of each color. There are 2 red marbles, 2 purple marbles, and 2 silver marbles in each of these drawers. So They represent the choices that can be made. We're going to go see it in action to start with. How it works. First, if you go rock, paper, scissors. Does anybody not know how to play rock, paper, scissors? This is really important for this part of the talk. I should not assume prior knowledge. The way you play is you say rock, paper, scissors, shoot. Depends on where you are, what rules apply. Different schoolyards play it differently, but most people say shoot and choose one of those three options to go with. So, come here, rock, paper, scissors, shoot. Going to pick one of those three. After it's picked one of those three, we're going to look in the drawer that corresponds to that human choice. So, as a human, I've chosen rock, and we're going to look in this drawer to pick out what our little robot's response is. From there, it's going to be a random selection, and based on what it chooses, we're going to either reward it because it won and it did a great job, or we're going to punish it for having done a poor job. So, over time, you will see this little robot gets better at playing rock, paper, scissors. Let's do an example. Rock, paper, scissors, shoot. Great. It's going to turn out to be rock because it has to match the slides. So the human chose the rock. We're going to look in the rock drawer. We're going to pick out scissors, turns out, randomly. Turns out that was scissors. What's going to happen from here? Did the machine win or lose? It lost, all right? So what do we need to do to it?
Punish it.
Punish it. Bad robot. It doesn't do quite well with, it does better with encouragement, I think. But anyways, rock beats scissors. We need to punish it. We're going to take away its silver marble. Turns out that we don't want you to do that. Whatever you just did, that behavior, don't exhibit that again. Just, I want you to take away from this experience. It's a learning opportunity. You know, we all fail. We all need to make progress. Don't do that as much as you did before. Let's do another example. That didn't sink in yet. First, before I do that, I need to talk about the numbers. What were the chances that it was going to win or lose? Well, the answer is, because of the slides, we knew exactly what was going to happen. But in the real world, if you were playing this game, it had a 1 in 3 chance of guessing the right response, right? So 33% for any one of those, what it could have been. Now that we've taken away a silver marble, when a human plays rock, it's going to choose that option less often, right? So now, and if you look in the top drawer here, there are only 5 marbles remaining. There are 2 red rocks, 2 purple papers, and 1 silver scissors. So 2 out of 5, that's 40% chance it's going to guess right if someone was to play rock. This little robot has taken its first steps in learning, if you will, how to play the game. So artificial intelligence is its own controversial word in machine learning. Is it really intelligent at this point? Is it more intelligent than it was before? At the end of the day, it's all just statistics. So let's do it one more time. Rock, paper, scissors. We chose rock. We're going to look in the rock drawer. We're going to take out, randomly, a purple paper. What just happened? It won. Good job, robot. You're getting better at this. Paper beats rock. We're going to reward it. How might we reward our little robot? Tell it it did a good job. This man's got it right. Give him more of that. Whatever you just did, I want to see more of that. You know, you're on the right track. You're starting to learn. Give him more purple rocks. So I have some extras over here. I'm going to give it another purple. Back in that drawer. So when we play next time, if you're keeping track, if you're keeping score at home, it has 3 purple marbles in there, and only 1 silver scissors, 2 red rocks. So these are the new percentages of how well it will do, how well it has been trained to play against a rock. Now, we haven't done any human trials of choosing anything besides rock. So has it gotten any better at playing the other outcomes? That's exactly where it was. So this is what they were talking about, biases in your internal data. If your training is biased towards a certain outcome, maybe your strategy on the schoolyard, as it was always to play rock. If you are the one who has been tasked with training this out of your outcomes, it won't learn to play very well against scissors and paper. Does that make sense? I'm going to slow down here and let people ask questions if that wasn't clear about how it's learning.
Is it really 50% or is it actually 80%? Because if you pull a rock, it's a stalemate, so it's not really a loss.
That's a great question. So what are we training this guy to do? We're training this guy to be average. We're training this guy to get a stalemate. We're training this guy to win. We want him to win. But that is really important, and we're going to come back to that. The intent of what does success look like? Is success getting it right every time? Is success just not losing? There's a difference. And you actually train it differently depending on what your outcome that you're shooting for is. So, very perceptive comment. Does that make sense to everybody? All right, we're going to come back to that. All right, if we keep repeating this many, many, many times, those numbers are going to start to increase for all of them. Assuming we play fair, we play all the different possible outcomes, it's going to only get better, right? How many times are you going to have to run through this training exercise for it to learn how to do this, to be perfect at it? Enough. Well, at some point, some of the training is going to become less useful, for example, for rock. If it just keeps getting closer and closer to that 100%, it's going to eventually start leveling off, where there's one marble left in that drawer that's still the other color that may come out. You don't really know when that one's going to come up. So that's where some of the uncertainty comes into. Exactly how's it going to behave? Exactly why did it choose this outcome this time? It's all statistics. It's statistically likely to get it right. If you do this long enough, eventually this is what the outcome will look like. There are exactly the right marbles in all of the drawers to make it work. Does that make sense? Great. Haven't lost anybody yet. This is going way better than the linear regressions would have.
So, if you had more marbles to start, that would take longer. So if we had started AI learning sooner, it would have less incorrect answers. Is that, I don't really know if I have a question, but.
No, absolutely. Verbal processing, that's how I do it too. The answer of what should be the starting number of marbles, how did we decide 6? That is what you pay the professionals to figure out for you, is how do you train it? How do you have the right number to start with? Those are all the parameters, the hyperparameter optimizations that you do, and trying to decide what model best fits this, how we're going to train it. Deciding it, maybe we shouldn't have trained it with just adding 1 purple marble. Maybe we should have rewarded it with 2 purple marbles, maybe 3. Maybe we should have punished it more severely. Those are all questions depending on your application. Some will produce much shorter training times than otherwise. So,
You add lizard Spock.
if you add lizard Spock, this gets more complicated, but you can do it. So that's a great question. It's up to you as the person training it. If you are the data scientist trying to teach this machine to learn, you've got to help it along. You've got to write the lesson for it. You've got to help it figure it out. So, part 2. There was nothing about trusses in any of that. We're about to turn 90 degrees and talk about trusses, because what the heck does any of that have to do with trusses? This is going to seem like a long tangent, but my hope is when we come back to putting these two things together, you'll have some sense of how an artificial intelligence might work, or machine learning, whatever buzzword you'd like to use. This is the sort of homework problem you guys do all day, every day. We have a failing truss. This truss design drawing says that there's a failure in panel 1 to 9. If you can't see that, it's the left one where the red lines are. There is too high of a CSI, 1.27 coming from load case 4. So, anybody else have failing truss designs? Never. Yeah, exactly. You guys have people that fix these. How would you fix it? That's how much it costs right now with the current failure. I should say you can't see it by color, but the chords are number 2. The webs are number 3.
Increase dimension size or add web.
That's right. Those are 2 things you could do. For anybody who couldn't hear him, he said you can either increase the dimension, make it a 2x6 or 2x8 for some members. You could increase the grade of the lumber for any particular member. Maybe you know which ones work better. You can add more members, right? You can have more panel points. You can increase the webbing pattern, or you can move the existing members around. In our example here, which of those is the most appropriate?
The one that costs less.
The one that costs less. Does that answer ever change?
No.
No, I heard a no. Did the lumber prices change at all in the last 5 years? Just a little. Was the pandemic an interesting time? We're going to find out. Normally, when I give this lecture, I've given it a few times, I hand out pieces of paper and say, everybody take your pen and see how you would solve it. We don't have time for that right now, is what Sean told me. But later, if you want to print this out and try it at home, you too can. Let's look at some of the solutions. So compare the results. Originally, it was failing with a bottom chord lumber grade of number 2. That was what it cost, $28.89. If we change the bottom chord to be number 1, it increases in cost to $32.83. So We made it pass. At what cost? Well, not that much. But the other option was to make it a 2x6. Now granted, these are just somewhat random prices I had in there, so for the particular pricing set that I had loaded at the time, these are the results of the different choices. So changing it 2x6 is an option. The other option is to increase the number of panels, add some of those webs in there. Usually webs are cheaper than cords, so depending on your price difference, how much waste you're trying to use up, maybe that's a better solution for you. Any other solutions that weren't mentioned before, if those didn't work or didn't seem like a good idea to you?
Optimize the bottom,
Optimize the bottom? What do you mean?
expand the points out, so you lower the grades on the outside and increase the one in the middle.
So for anybody who didn't hear that, his suggestion was to move these joints outwards, those panels that were failing, make them shorter. So that's typically the engineer's response. If you've got too long of a panel, make it shorter. What's really interesting, we're going to see in a moment, is actually there's a better way, and it's moving the joints the other direction. So the only answer is you've got to try them all before you really know what was actually optimal. Turns out you have to just go through and guess. All right, well, if we try this, what's the end result going to be? I think many of you employ optimizers whose full-time job is to go and do that. Take the building, how can we get more wood out? Optimize it for your operation. Which of these actual configurations is best for what you're trying to do? Usually you're under time pressure to get these things back, and you're not limited by the things you could try, you're just limited out of time. You ran out of opportunity before you had to turn it back to somebody. So the surprising solution is actually to pull the joints closer together. Who can tell me why?
Cantilever effect.
Cantilever effect, good guess. That is not the right answer though. My brother, you can't answer because I think you know the answer. Is that anything anyone would have guessed? Making these panels that were failing longer actually makes this pass.
Made it from going from being in compression to tension.
Nope. Nope, not the analog.
Did you have splice on the bottom cord?
Yeah, there's no splice on the bottom.
There's no splice. That was only made for making my example work. Don't ignore that. That doesn't actually affect it. The surprising solution comes from the building code in IBC. Uninhabitable attics without storage and with storage. Where there are two or more adjacent trusses with web configurations capable of accommodating assumed rectangle of 42 inches in length by 24 inches in width or greater within the plane of the truss. We move those things just close enough together, that box does not fit anymore. We no longer have to run that load case because it does not fit. As a human, you can do that right now, can't you? If you had thought to try it, you could play with things, move them around a lot of different times, and eventually end up in a result. For whatever reason, we just made this truss stronger by making the not intuitive engineer result of moving things closer together. It's in your software right now. I guarantee if you go try that, you're going to get the same result.
You didn't make it stronger, you just
You just ignored the code.
moved one of the load cases.
Yeah. So like I said, how should we feel about that?
Feel pretty good about it.
I hear that's the right answer. Made it cheaper. Turns out we did not increase any of the material sizes. We didn't change anything about it other than just move those closer together, and the problem went away. So yes, it's different load cases. Turns out the answer, that's the hint over here. It's without storage now. So starting to get into what you should be afraid of with artificial intelligence is, was this the intent of the building code? You know, it turns out if it's 41.99 inches, we're good. We don't have to run that part. Now, luckily, no homeowners actually stick a box that's 41.99, only 42. There are a lot of prescriptive solutions like this that end up being what's called a decision boundary for an artificial intelligence. It just knows I've been rewarded when I do things like this in the past, and these answers work great. I got rewarded. They said I did a good job when I moved these things closer together. Why it did what it did, it doesn't know. It's statistics. Statistically likely, I got the result out the other side. The cost was lower, so I just decided to do it. Does that make sense? Are you all going to go back home and tell your optimizers to start just moving panel points around, see if you get a better result? I hear we already do. Yeah, great. See, there's nothing new or different about anything in that example, other than in the future that's coming, and is in many ways already here, trying many, many, many possibilities is going to be way cheaper and much faster. Because the human won't have to be the one that moves it, hit analyze, moves it, hit analyze, and see what the results are. So, wrong button. Is this optimal? Are there any architects in the room? I will not say your name if you were the one that prescribed this building. At some level, being a trust designer, there's a level of intuition you build up to be a skilled designer of knowing what the right answer is. There are certain shapes that become hard to reason. Does that intuitively look right? You don't know as a human. At some point, it's really hard to investigate all there is to know about a truss. So that's just on a single truss. We're not even talking about a layout yet. Now let's turn our attention there. You've got this building. Is there a right way to lay this out? How many different iterations do you do of a layout on a building, laying out your trusses? The options of what you can tweak in this world are the direction of your trusses, how long you're forcing them to span. How far, what's the right answer for how far back a hip girder ought to be? What's the setback?
Whatever the cheapest version is.
Whatever the cheapest version is.
It doesn't land on top of a window header.
That's right. There are other considerations, and we're going to come back to that too, because that's the job of the ceiling EOR, to figure out all the load path of a building, not truss designers. So it's one of those where it matters if you know all that information. Often you don't. Often you aren't handed all of that up front like you should be. So depending on what part of the country you're in, you probably have different standards of what you tell people to try first, what your setback ought to be. If you're in a high wind zone and you're really concerned about uplift, turns out the more expensive thing you're concerned about is if I choose this setback over this one, I'm going to be requiring more expensive connectors to prevent the uplift. If you're in a region where that doesn't matter, maybe the answer is different for you what the best setback is to use. And granted, I am confident your designers don't have time to try 6 feet, 6 foot 2 inches, 6 foot 3 inches. There's just only so many possibilities you can use to find what is the actual cheapest result. Oh. Which one that uses the least amount? If lumber is your most expensive part, and traditionally that is the most expensive part, but what the right answer is as far as what your entire, it's going to be different by shop, right? How many sizes do you keep? How much reuse of wood do you use? Lumber is the consideration. Something that we haven't touched on here, but lumber in your truss or lumber required for bracing, lumber required where? There's a lot of things that you've affected by what choices you've made here. It's not just the trusses that get built. It's the framer who's often most impacted by what decision you make.
Size of girder is required to carry the full amount of area that is created by where you place the girders.
Exactly. Was it better to have more plies in your girder or was it better to have shorter jacks? There's a lot of variables to this that get hard for a human to do. Something we didn't touch in the previous example of how to make that truss pass. You could have made your truss multiple plies. Normally that's a pretty drastic option. You could change the spacing so that you get them close together. That can work, but pretty drastic solution. Is this optimal? This man says no. What should change about it? The correct answer is we don't know. Not enough information given. It depends on the parameters for this particular project. As it's hard to tell, just as a human looking at it. So it's a hard problem for a human to be able to tell exactly. It doesn't feel right. I've looked at enough of these designs. Something is wrong. What does it need to be? Well, maybe the numbers worked out that this was the right answer. Who knows? So any questions about that before I move on from the truss part and try to bring what we talked about at the beginning, which may seem completely irrelevant to what we just talked about there?
Also,
So what to fear about AI? Like I said, all of these opinions are my own, but this is what I would lead you down. This is going to seem like a totally another random trail, and I promise you it's all going to come back together here in a moment. What is the best search engine? Does anybody have an opinion? Is Google the best? Raise your hand if you think Google is the best search engine. No hands. Oh, we got one. Raise your hand if you think Bing is the best search engine. Microsoft Bing. No, no hands there. All right, what is the best search engine in y'all's opinion? It looks like we've got a variety of answers.
DuckDuckGo.
DuckDuckGo. That wasn't included on this piece of photography I grabbed off the internet, but yes, there are lots of reasons. Why is DuckDuckGo better?
It doesn't record where you go.
Doesn't record where you go. Do you trust the results to be less influenced, perhaps, by the agenda of the people who are building it? If you have other products to sell, it might make a difference of what order you return search results. I think the closest example I could find to try to explain what fears you already have about large companies like Google or Microsoft. If you type in the search box, word processing or document editing software. What do you think is going to place higher between Google and Bing? Well, it depends on which one you're picking. Microsoft probably shows theirs higher than Google Sheets and vice versa. You start to have some level of doubt that they're aligned with you and having the same interest. I want the best tool. Well, as we talked about before, the best tool, what the right answer is, what was the tool trained to do in returning the answers, depending on who is answering it, changes what direction it's pushed, what the right answer was. I don't know if anybody's familiar with Baidu, the one on the bottom left, the one that has to be used in China because there are other rules that apply there of what the right answer is in search results. Yeah. You can imagine there's often an agenda behind a tool that you might say, well, tools, they're not right or wrong, they don't have an opinion, they're not good or evil. The ones who make them, depends on your perspective is the answer to a lot of things. So back to our example with our little robot friend here. I used to have some little googly eyes I put on to make it a little more personable. Like I said, right now you think he's just a machine, right? Well, turns out he has more of an opinion than that. It depends on who taught him what he knows. So can we train it to do other things besides just win? Back to your earlier comment. What if we want it to always lose? Maybe our motivation in making this tool, it's really a product that's intended to increase other people's self-confidence. Maybe the goal is we want to train it to always lose. How would we do that? Well, you would reward or punish different behaviors. So I just swapped the arrows from what was on a previous slide. If every time it played rock, when you played scissors, well, that would mean that it won. Sorry, did I say right? Yeah, that would mean that it won. You could punish it for that. Punish it when it wins. It doesn't really know. It doesn't really care. It just knows what you've told it. I gave you more marbles when you did this. I gave you less when you did the other. It can be more than just winning, losing, or stalemating. We'll talk about in a moment. It can be a lot more things. We're going to take 3 different scenarios here. Rocks Rock Inc. If you were handed this robot from Rocks Rock Inc., the same way we were just talking about Google, Facebook, Microsoft, do you think it would be producing a particular result more often than others? Or might be a temptation to train it? You know what? People, when they see more rocks, marketing studies have told us they buy more rocks. If we just have that be the answer, no matter what you play, always rewarded if it played rock, punished if it played anything else. Maybe, for whatever reason, you decide you want to train it to do that. Having an agenda. Super Scissors Inc. Kids these days, they're not allowed to run with scissors. Maybe we need to get in that market and encourage kids. Whenever scissors are played, we don't want it ever to play scissors whenever rock's involved, but the other times we actually want it to turn out to be that choice. You can reward it in ways that don't necessarily line up with any particular one outcome, but I want it to win 20% of the time. I want it to win 30% of the time. Depending on how you reward it, how much you punish it, it can come up with whatever result you want it to as you train it. So that's where randomness comes into some of the equation of, if you're trying to get a very, non-obvious result, randomness turns out to be a really useful tool in addition to what is the starting statistics you set it at, what state. Turns out setting it at a random state helps you train things like this faster. There are some properties that's what a data scientist typically studies. Does that make sense? The correlation we just tied here from our fictitious example with our product with Microsoft and Google and all the rest? Great. So back to talking about trusses. Optimizing for whom and what? We talked about optimizing lumber. Who cares more about the spacing? We don't care about the spacing as much as the framer does, right? Trying to get it right. Like I said, I walked through one building and we'd seen the floor trusses were set 1 foot apart. It was really hard to get the HVAC in. They actually had to cut a hole on the outside wall in order to get it into the chase. Because that spacing, I didn't think about that when I was looking at truss design, but turns out I've not had any experience framing. Turns out they care what the spacing is. They care that the number isn't 1 foot spacing here, 2 foot spacing here, wherever else. They want it to be predictable. Has anybody ever seen a truss that is flipped end for end and should not have been? Turns out that's a common thing on symmetrical trusses that look symmetrical, but they aren't. Turns out they're easy to turn flip end for end. So pretty much everything when it comes to labor, the opaqueness, where it's really hard to back into and it can't tell you. The people who made it really can't tell you. They just know statistically in this situation, that's what it came up with. You've heard the term hallucination. The AI hallucinated. Yeah, that's what they mean. It came up with the answer that we don't really expect that it would have in this case. We don't think that's the right answer, yet that was the result it gave. So the conclusion, don't fear the technology. It's not how the magic trick is done, the underworking parts. If you didn't catch that, now's the big reveal. Whenever I take my hands off from doing this and point at you, I don't put my hand back the same way. I put it here and turn it upside. Like I said, that part's not scary. It's the larger impact, right? So do fear AI without transparency. Do fear AI that has an agenda. And you may not know what it is. So if you're using an AI tool, seeing who you're buying it from, right? What is their end game? What does success look like for them? That'll help you make informed decisions. That's one for agenda and something I left off for transparency, tying it back to the building code. We had a little bit of back and forth. Is it the right answer to ignore that section of the building code by making things fit there, by making things just move? Sometimes even the people that build it don't understand why it kept choosing to move those joints closer together, right? They just know that produced a cheaper truss. Are there other prescriptive provisions in a building code that produce a result that's actually less desirable, that don't match the intent? It has no intent. These machines are not sentient. They don't have an opinion. They just know what they've been trained to do. So this is the end of my talk. If you want to learn more about artificial intelligence and our product, Paragon Dan, you can come to our innovation booth, 1507. There you go. So we can talk about this all day. This is one of my favorite subjects. Now, any questions?
So it's just a little bit of verbal thinking out loud.
Yep.
So it seems like even from a material standpoint, I was going to say, I stock this size of lumber at these different grades that I think is optimal. But if I could tell the machine, hey, take every job we've done in the last 12 months and tell me what grade and size of lumber I should be stocking to actually be the most efficient.
That would be a great use.
Or plate sizes.
Yep. Very much so. Because it's the sort of thing where we start using rules of thumb, right? We've done this. The rules we learned when we got started in this industry may not be the right answer in a time where lumber prices have skyrocketed. That rule of thumb doesn't apply anymore. They're ever volatile. They're ever changing. When you change out a piece of machinery in your plant, all your numbers that you had previously for your time and motion and the rest, it's not different. You have a different bottleneck than you had before, perhaps. I really appreciate y'all coming.